Well, hello everyone and welcome back to Adrian's Digital Basement. This is part 2 of the TI99 repair series, I guess we're going to call it. In this video, I'm going to try to see if I can troubleshoot this TI99 that a viewer sent me a while back. Let's get right to it. Alright, did some Googling around and I found the Home Computer New Technician Guide. This is for the TI99 4A specifically. There's a lot of great information in here. It's actually an interesting read. So one thing that's different about it, even though it's relatively old, is it has a 16-bit microprocessor, a full 16-bit microprocessor with 16 data bits. You see it says D0 to D15 here. To save cost on this thing, it has an interesting design. Well, you'll notice it has 4K by 16 of ROM, so this is actually 16-bit wide ROM. And then it has a small amount of work RAM here, some kind of high-speed RAM connected to the full 16-bit data bus, 120 bits times 16, which I think comes out to, what, 240 bytes of RAM, something like that. And this is enough to get the computer booted or starting to boot. And then the rest of the RAM is up here connected and hanging off of the video display processor. That's the chip I've already changed. This has an 8-bit data bus, and the video display processor is also connected to the data bus just with the first 8 bits. And then down here is a 16 to 8-bit interface, which converts the wide 16-bit bus just down to 8 bits to run things like the sound generator and the additional ROMs to boot the computer. It's the expansion port connector for the cartridge, that is. And over here on the left is the TMS9901 I/O controller, which seems to interface to the keyboard and the joystick and stuff like that. I'm assuming this has a data bus connection as well. It's not shown here because this is the address bus going into here. I'm assuming there's more to this, but maybe not. Maybe this is doing some weird trickery on the address bus. Now there's something I haven't tested yet. The sound generator chip is a TMS9919, but it's very similar, or it is the same as the chip that's in the Tandy 1000. And what's interesting on the Tandy 1000 is when you first turn on the computer, you hear a tone out of the speaker very briefly, but as the computer initializes, it shuts off the sounds from the chip. If there's a problem with your Tandy where it's not actually initializing the ROM, so it's not booting at all, what happens when you first turn it on is you just get a continual tone. Now, way back on my channel, I troubleshooted my Tandy 1000EX, which I got for free because it wasn't working. And one of the problems on that, when you turned it on, you got a black screen and a continuous tone. And that was because one of the custom chips on there that kind of generates all the clock signals for various components on the motherboard had gone bad. And since this is using the same sound chip, I need to turn on the speaker and listen when I turn this computer on and hear if it is actually initializing this sound chip, or if it's not, that would imply that it's actually not even getting to the stage where it shuts that off. Now here on the video output, I've connected my speaker and I've turned the volume up on it, so let's turn the power on and see what happens. There we go, we're getting continuous tone, which implies that sound chip is powering up and working, but it's not getting initialized, so the computer's not booting at all. Let me try turning it on one more time. Yep, and it's slightly different, the tones each time. And what happens with this chip is it boots up with random data in the registers, which is what creates those random tones, and then it's the BIOS or the ROM's job to shut that off. Now what's cool in this document is when we scroll down here, past this additional stuff, look at this. Here's the system power-up routine. So power is turned on and the 9900 CPU resets and addresses the low EEPROM locations. The CPU initializes, it sets up the workspace registers in the 6810 RAM. That's that 16-bit work RAM I was talking about. 9900 begins reading from GROMs. Now the GROMs, from my understanding, are high-speed ROM chips that are connected directly to the 16-bit bus, and they're small and they're needed to get the system booting, and then after that it reads from the regular ROM. But let's keep going down here. 9900 enters the time delay loop to allow stabilization, quarter of a second, so I guess that's like to stabilize the clocks or whatever. 9919 sound chip is turned off. So this is the step where it should silence that chip. Next thing, 9918 VDP is initialized. That's the video chip I just changed. So it's not even getting to the stage where that chip is initializing, and I switched it out, but it's actually getting stuck before the sound chip is turned off. Now it says 4027 RAM is cleared, requires approximately 1 second. I think this is referring to the 16K of RAM, but on the original prototype board, it only had 8K, or on the original TIs, and I think this was the part number. But this is clearing that RAM, takes approximately 1 second. Front panel display is written to the VDP. I think that's like the initialization startup screen. It's like a welcome screen kind of thing. And then the sound chip emits a beep, and then it starts scanning for you to press the key to continue booting the computer. So from the symptoms, we know that it's getting stuck before it even gets to the sound chip. So it's something in here that's having a problem. Okay, well look, I just scrolled down a little further and here's a nice troubleshooting checklist. Step 1, check if the front panel is up, TI logo. So nope, that's not happening. Check the plus or minus 5 and plus 12 volts throughout the board. Okay, well I checked it on the one connector, but I need to go through and just check it to make sure that it's visible on the CPU and the other various things. Because if we look at the board here, these blue wires that sort of run around the board, I think this is carrying some of the voltages around, not to mention these white bars here are doing the same thing. The next thing is to check if the ready pin on pin 64, the 9900, that's the CPU, is locked up. And then the next step is check the 4 12-volt clocks from the 74-362 to the 9900. So the 74LS362 is this custom chip that TI made. It generates the 4 clock signals that this processor needs. There's 12-volt clocks. I think there's also 5-volt clocks that come out of this thing on 8 different pins. So it's telling us we need to make sure that those 4 12-volt clocks that go to the processor are looking good. And then those ROM chips, which are those special high-speed ROMs, have additional pins. It's not just like a chip select. It has a select, a ready, and a clock signal as well. So that's telling us to check those pins as well on those chips. And then it goes into checking the clock signal, and then checking the VDP, some stuff on there, and on and on and on. Okay, so look at this. This is the 4-phase clock that it was talking about. So there's 12-volt clocks and there's 5-volt clocks. 12-volt clocks seem to go positive. It looks like it's up to nearly 12 volts, and there's 4 phases and it repeats. And then the 5-volt clock is the same thing. It's a negative trigger clock, so it's usually high, and then it goes down to trigger, and there are 4 phases, and it just repeats over and over again. So I also found this handy tool here, which shows the motherboard, and it shows you what every component is. So for the GROM chips, which we're going to have to look at and troubleshoot, it's number 4 here on this chart. And so 4 is on the PCB, and see this box around here? It's these 3 socketed ICs. These are the GROM chips. Now, unfortunately, I don't have my other TI99. It's at work, and I can't swap these chips with the ones from that. So of course, if these are bad, these are bespoke chips, and I have really no way to try a replacement. Maybe there's a way to like hot wire in a regular EEPROM into this, but I doubt it because these have clock signals and all this other complicated stuff. Down here, chip number 7, this is the clock generator, which makes sense. It's right next to the crystal oscillator. Up here, number 5, this is the sound chip. Yeah, it's a little tiny chip, but this is the same size as the one on the Tandy. All right, I did a quick check of the voltages and everything looks good. I'm seeing the 12 and the -5 on the RAM and the +5 and the same on the clock generator chip and on the CPU. So I think things are looking good from a voltage perspective. That was the second step on the troubleshooting. Let me move to step 3. Check if ready pin on pin 64 of the 9900 is locked up. Okay, so all the voltages look good. Now I've broken out the logic probe and it's time to start checking these pins. So I've looked in the troubleshooting instructions after the voltage. It says to check that pin 64 is high. And I'm looking here at a pinout of the processor, and 64 is a signal-enabled hold. And it says hold is active low. Hold indicates the processor is in an external controller, i.e. DMA device, desires to utilize the address and data bus. So when this signal goes low, it halts the processor so other things can control the bus. So this needs to be high for the processor to actually stay running. And it's high, so that's good. That's what we want. And then I noticed that pin 6 is the reset signal. And if we scroll down here to reset, it says it's active low. So reset causes the processor to be reset and blah, blah, blah. So when this signal goes low, the processor will be held and will not execute. So if I check that signal and it is low, well, nothing's going to work. Also, it should stay low for a split second and then come up to high when I power the computer on. So I'll power it off. 1, 2, 3, 4, 5, 6. And now let me turn on the power supply and it should go low, high. And it does. You hear that? So that's normal operation of the reset circuit. So the CPU is not being held in reset. All right, next step is to check the 4 12-volt clocks coming from the 74-362 clock generator. That's this chip right here. And I'm going to need to use the oscilloscope to look at these clocks because it looks like this. And to check all 4 phases are working, I'm gonna have to go through this. Unfortunately, this will tell us if the clocks are there or not, but I won't be able to see if they look good. So on the iPad in this document is a picture of the clock generator, and unfortunately it's so hard to read, but I can see there are 4 pins here that say TTL, so those must be the TTL clocks. And then these 4 pins are going to be the 12-volt clock output. Now there's ground, there's VCC. So I'll first start with the logic probe. We'll just look to hear the beeping. In fact, I might as well go over these TTL clocks while I'm at it. So starting at pin 6. So that's pin 6, it's pulsing, that sounds good. That's a TTL one as well, it's beeping, so that's good. That's one of the 12-volt clocks, so that sounds good. That one sounds faster, but I'll need to look at the oscilloscope to see if it's working correctly. And then this one. They're all beeping, so that sounds normal, but I'm gonna need to check with the oscilloscope to see for sure. Okay, so here's the oscilloscope. Sorry, I don't have 2 cameras set up, so you're just gonna see what I'm probing here. So I'm gonna check the 2 TTL clocks, then the 4 12-volt clocks, and then the 2 TTL clocks. I'm gonna go around the pins, and let's start. All right, there's the first TTL clock. Now it's 5 volts per division. Let's turn this up so you guys can see a little bit better. And we're getting exactly 3 megahertz, which is exactly correct according to the schematics. So that looks good. Let's check the next 5-volt clock. That looks good as well. And then here's a 12-volt clock. And remember, it's the opposite of the 5-volt clock. So the pulses go up as opposed to going down. And it looks good. It's exactly 3 megahertz. This is the next pin. Also looks good. 3 megahertz, 12 volts. That looks great as well. No problems there with that one. That's the last of the 12-volt clocks. And we have a 5-volt clock, the third one, and it's looking good. See, it's going down. It's kind of active low, I guess it's called. And that's the 4th and final clock, 5-volt clock, and that also looks perfect. You may have noticed on the waveforms there's a little bit of overshoot. You can ignore that. That's just because the way I had the probe connected with this long ground lead, it's not ideal. It's good enough for this purpose, but if you're doing a high accuracy measurement, you can't hook up long wires like this. Okay, back at our checklist. Number 4 was check the 12-volt clock, so we can check that off. Those look good. Next is checking some GROM signals. So select, ready, and clock on pin 13 on the GROMs. So it's talking about GROM pins on 0430. I don't know if that's one of the chips. None of these chips have that marking on it. So I'm going to check to see if those pins are actually have continuity between them. I'll use the multimeter for that. Okay, let's see if pin 10 has continuity. Yep. So that one's connected to all 3 chips. Pin 13. Yep, that one is also connected through to all of them. And so is pin 15. Okay, so I don't need to worry about which chip I check it on. Those signals are going to be on all of them. Now, it's vague about what I'm looking for. It just says check, select, ready, and clock. I mean, I guess clock should be pulsing. Ready and select or doing something. I don't know. So let me just test those out with this probe, and we'll start there. So 10 is high, and that implies that that is the select pin. Let's turn it off and on. Just goes straight to high. 13, which is the clock pin, sounds to be pulsing, which I expect. In fact, when I first turn the computer on, it goes solid for a second, and then it starts pulsing. So maybe that's normal, I don't know. And then there is the ready pin 15. So that's just low. And it just comes on to low immediately at power up. So I'm looking at the power up sequence, and it says sets up workspace registers in the 6810 RAM. That's this 2 SRAM chips here. If either of these are bad, I think that would prevent the computer from booting completely. In fact, it doesn't even get to the GROMs yet until it's already addressed these RAM chips. So I should probably check out the pinouts of this and check all the data and address lines on these to see if I see normal activity on them or any are stuck. Okay, I've looked up the pinout of the 6810 IC. These are all the data lines 0 through 7. There are chip select lines. There's actually 5 chip select lines. Well, 6, 0 through 5. There's a read-write pin, and then there's A0 through A6. Let's give it a check. Although the chip is mounted in the board like upside down with pin 1 being down here. So I'm going to start with the address lines because we want to make sure all those are working first before we get to the data lines. Because if the address lines are stuck, the data lines aren't going to be doing anything either. So we'll start there and we'll go through them all. Now they're all going to be parallel, so I don't have to check both chips. The data bus lines, we have to check both because one chip is hooked up to the lower 8 bits of the 16-bit bus, and the other one is hooked up to the high bits. But the address lines are all parallel. So let's just go through those real quick. Okay, so all the address lines are looking normal. In fact, so are the chip select. I'm seeing kind of stable signals there. And read-write also is toggling, which is normal. If it's trying to write to the RAM, the read-write pin is going to be changing, right, as it reads and writes. Now let's go through the data lines. So that's ground, so that's going to be low. And then we have this one. And data bus 0 is just low on this chip. It's stuck low. And that does not seem normal. Line 1 is pulsing. 2 is pulsing. 3 is pulsing. 4 is pulsing. 5 is just solid. So that seems weird. Solid low. And so is 7. So 3 on this one are stuck low. And on this one, 0 is pulsing. Pulsing, 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 pulsing. That's fine. Those sound weird. So that one, everything seems to be doing stuff, although you heard the sounds this thing's making are a little weird. So I think at this point I need to look at the oscilloscope on these two RAM chips and check out these lines for ourselves visually. Okay, one camera setup. So again, we're only going to be looking at the data lines. First, I'm going to start with the right chip, and I'm going to go through 0 through 7, and we'll take a look at what each one looks like. Data line 0, that's fine. That doesn't look out of the ordinary. We're at 1 volt per division, so we got about 5 volts there. Now this looks a bit strange. What's going on here? Now this could easily be because the data line is floating, like nothing's connected to it. And we do see a high and we do see a low, and that seems fine. So I'm thinking this is a tri-state bus and this is just floating. So that's not that big a deal. This one looks fine. This one looks okay. Here's another one where it's sort of stuck in the middle. Now it's weird how not everyone is doing that. So I'm wondering if this actually indicates a fault. Okay, so this is data line 5. This is not normal. Something's wrong on this data line. This is not going all the way up to 5 volts. It's lost trigger, which is why it's moving, but this is a problem right here. Something is definitely wrong. On this bus is probably the ROMs. There's a few components on it, right? And there could be many things that cause this particular issue, but there's definitely something wrong on the data bus, and that's going to prevent this computer from booting. The next line also has the same issue. Look at this, something's wrong here. And then data line 7, this looks normal. So it was data line 6 and 5 on the right chip that were screwed up, and then a couple of them also had that weird middle section. But because I saw a high and low on those, I'm not going to say that those are totally broken. Now on the next chip, this is one of the ones that's just held low. This does not seem right. I am not expecting to see that on the bus. This looks normal. That's data line 1. Data line 2 looks absolutely normal. 3, that looks normal as well. 4, that's fine. 5, this looks really screwed up. This looks exactly like 0, like it's trying to drive it and it can't. In fact, if I move the trigger down, you can see that where the other ones were pulsing up to 5 volts, this thing is being stuck down at 0 volts. And then this line is also screwed up. This is data line 6, it's messed up. And so is data line 7. Wow. So we've definitely identified that there's a fault on this motherboard. Now, unfortunately, when you have faults on the data bus, they're not easy to figure out because it's exactly what it says. It's a bus, and there are a bunch of things connected to it. If we look at this dock diagram, there's 2 additional components on the bus. There's the video display processor, and that's on bits 0 through 7. And then there's also the 16 to 8-bit converter device. So realistically, the video processor could be faulty, this converter could be faulty, the RAM or the ROM or the processor. Any of those can be having an issue, and that could cause those issues on the bus. First, I'll take out the video display processor because that is in a socket and is easy to remove. Okay, back to the one camera setup. Let's go through these data lines and see if there's any difference. First, the right chip. Oh, I just had a thought. You know what? Okay, so I think taking out the video display processor has caused the computer to not do anything at all, because I'm pretty sure this generates the clock signals or something that's used for operation of the computer. So without this, we get nothing. So what I'm going to do is I'm going to reinstall the original chip, not the one that I've changed it out to. Let me touch this. The probe is a good way to tell if the computer's on. So if it's on, I can't tell, right? But it beeps if I touch it. So double check that first by turning it off. Okay, so I'm going to reinstall the original video display processor into here. Okay, so the original's back in there. Let's turn it on. Okay, we're getting beeping, so let's just check that these are pulsing. Yep, so we're getting signals back on these chips again. So you have to have the VDP in for the computer to do anything. Good to know. Okay, first eye on the right chip. Okay, that looks the same. Same. Okay, that looks worse. Okay, so I'm on the right chip, and it definitely wasn't doing that. Let me turn it off and on. That's like some kind of a short or something now, and it was not doing that with the other VDP. Okay, so that's data line 7 on the right chip looks good, but 6 does not look good. That looks very screwed up. And 5 looks really screwed up. I mean, at least it's coming off of ground, but where's the signal? What's happening here? This also just looks quite different than it did with the other VDP. Let's check the other chip. Okay, data line 0 is screwed up. It's held low. And we're getting pulses there, so that's okay. Although notice it has a little bit of screwed upness there, so maybe that's normal, I don't know. So that looks really good. That looks like a good signal. That looks good as well. That's good. That is not good. That's just like it was on the before with the other VDP. It's sort of just stuck low and stuck low. And if I turn the computer off and on, oh, you do get a quick pulse of 5 volts actually. Interesting. So briefly you see 5 volts. And then it gets stuck low. And this one, same thing. So on the left chip, all these ones that are stuck low have a brief high pulse and then they drop. Right to the right chip, this does not look right. Let's turn it off and on. Actually, we were seeing this on the other VDP, right? Let me swap back to the other one, just make sure that this signal looks the same. Okay, I've switched back to the VDP I got in the mail call video. Let's look at these pins again. Okay, so this is the right chip with the other VDP, and we're seeing the exact same thing going on here. And this pin as well is screwed up. Okay, so I saw absolutely no change with the two VDPs. Both of them look the same. The signals definitely look screwy, at least the data lines. And that, I'm not pointing out that it's definitely these RAM chips, but something is the matter on this board. So really at this point, it's a guessing game for me as to whether I should remove the RAM chips and socket them or remove these 3 bus converters and socket them. And I mean, I don't have another CPU. So if that's the problem, then there's no point for me to socket that thing. Not to mention, I think I do have a socket for this because the same socket has a 68,000, but I think the most likely candidate for a problem is going to be these RAM chips and maybe these transceiver chips. So let me go look at what these transceivers are, and if I have some of those in stock, maybe I'll pull those out as well and put sockets in. Okay, those of you who troubleshoot the TI were probably screaming at your screen. So these 3 chips are the GROM chips, but I was kind of dumb in interpreting the instructions because these 2 ICs here are ROM chips, and these are on the 16-bit bus with the RAM chip. So these 4 ICs are all hooked up directly. So the ROM is split into 2. I think they're 4K each, and there's 2 of them. So absolutely, positively, the ROMs could be the problem as well, and the RAMs. I'm assuming these are maybe, hopefully, standard-ish ROM chips, although they might be the equivalent of a 2316. So I need to look at the pinout of these and see if I could replace these with EEPROMs. So I'm really struggling without the schematics. I need to try to find the schematics for this board so I could see if these ROM chips can be replaced with standard EEPROMs or if I'm going to be dead in the water. In fact, I mean, honestly, I don't even know if I have any of these SRAM chips either. So at this point, I'm probably stuck, but it's worth a try to see what these are and pull them out of this board. All right, I looked back at the FTP server where I was reading that original document, and there was a second PDF which I didn't open. I don't know why. It had the same name. It looked like it was just part 2, which is actually what it is. And what you're looking at here is a much more comprehensive flowchart about how to double check the computer. So, the first step here is front panel comes up, which is the text screen, and that's a no, right? So, check power supply, which we did. It looks good. So you go down to here. Check all the clocks, which I did, and they all look good. So you go down to here, it's telling you to check more pins, clocks, which are fine. So it says go to page 3. Now it says check pin 62 on the processor for the correct ready signal. And there's this picture here, which is so hard to read, but it's an oscilloscope reading showing the ready signal, which is pulsing. And I guess it's supposed to look like this when the computer is working properly. Well, I checked it, and this is currently in stop mode, but basically this doesn't look anything like the picture in the document. So we go to no, which is here, check the reset for the high level, which I did, and it's correct. Remember, it goes low, high, so we know the reset working. So we go down here, it says, pull the GROM sound chip and then check ready good. Well, the GROMs are out of the computer and the sound chip is not. I'm going off the assumption that this is how the ready should look, and it doesn't look like that on mine, so it's a no, no, no all the way down here. And it finally, you know, it's going to AA, it says, and we go back to AA, and here we are back at the start of this thing where it's checking the ready signal. So let's go off the assumption that the activity I see on mine is ready is looking good, right? So we're going to go from ready over to here, check pin 5 of U601 for high level. And this only has like a couple outcomes, right? It wants you to check a signal here, and it wants you to check some other stuff here. And then it says U601 is the probability. So let's look at what U601 is and these other things here, right? I mean, I don't know. I think I'm going down a dead end with this, and the troubleshooting I did earlier showing that the data lines are screwed up is actually more an indicator of a problem. So luckily I found that if we scroll down in this document, there are actually schematics in here, so that's excellent. Now what's really frustrating to me is the schematics has some chip markings. Okay, so it doesn't even tell me what chips are what, but it doesn't even matter because nothing is labeled. There's no silk screen whatsoever on this motherboard. So it's really difficult for me to know where the chips are. Now in this second document, there's actually a layout of the motherboard with the chip markings, but it is so difficult to read. U601, it says here, is the 74LS362. That's that 4-phase clock generator, which we already checked, and those clock phases look good. So there's nothing wrong with that. And it's funny because it says that that should be in a 20-pin socket, and it is not. It is soldered onto the board. But it's so not helpful that I'd like to know which chip is where, and it's basically almost impossible to read this scan. Or at least in this part of the schematic, here's the CPU over on the right. These are the two RAM chips, and these are the two ROM chips. So at least I can see how those are connected to the bus. And what's going on here, so this is data lines 8 through 15. So this is those high bits that can't get through on the 8-bit bus, right? Because you need a converter to that. So they flow through over here to this LS244 and this LS373. This is a latch. And these lines from up here are from an LS245, which connect the top 8 bits to the bottom 16 bits, that are the other half of the 16-bit bus. And these 3 chips are what interconnect these 2 buses and allow things that are standard 8 bits to communicate with the 16-bit processor. This does absolutely confirm that on the 16-bit data bus, all that resides on that is the video display processor, which is going off here, off to a different page. And then these 3 ICs and these 4, the 2 ROMs and the 2 RAMs. So there's a fault in one or more of these chips on this data bus that is causing this computer not to run. And I am pretty sure that if I figure out which one of these is bad and I fix it, well, that should make this computer work. I've already ruled out the video display processor because we've switched both of them and it doesn't change the bus problem. I could swap out these 74LS 245s, 244, and 373. Those are standard parts. I have lots of those. So I could switch those out with known good ones. Now, with at least 2 of these chips being problematic, or the CPU being bad, or 2 of these other chips, I have to just start guessing and unfortunately start taking these off the board and seeing if the problem goes away or stays. And that's really, unfortunately, the only way I can do it. There's something called a current tracer, which could help you determine if a chip is holding a line low. It's basically fighting against the CPU, and you can figure out which chip it is with those types of tools. I don't have a tool like that, so there's no way for me to do it. Now, sometimes if things are screwed up, one of these chips will be running hot, right? That's where I did at the beginning of the video. You could touch it if there's a short internally that's causing those lines to short, but clearly whatever fault is going on, it's not all the data lines that are screwed up and they're all connected to all these things, right? It's a couple of the lines that are bad. So at this point, all I can do is start to try to figure out what's bad by pulling chips. All right, you may notice that these three ICs are in sockets, as are the two RAM chips. It wasn't too difficult to desolder. Okay, we have the scope probe, and I'm expecting to see the same issues on these two SRAM chips when I check out those data bus lines. Data bus 0 looks the same. 1, well, that's screwed up just like it was before. 2, looks like it's working okay. That doesn't look right. And that one looks screwed up. Okay, and then the left chip, this pin should be bad. Yep, down by 0. This pin is okay, and it is okay. Okay, all right, that's good. Okay, that's good too. And should be bad, and the next one should be bad. And it is. Okay, so everything looks basically identical to how it was before I socketed everything. So there's a couple things to try. First, I could try swapping the two RAM chips around and see if those bad lines follow the chips or stay in the existing sockets. That's a good test, because if we switch these two chips and nothing seemingly changes, then I know the problem lies elsewhere, either with one of these three ICs here, or it could be the ROM chips, which I didn't pull out. You know, I don't know why I didn't socket those. I should have done those at the same time. Okay, the RAM chips are swapped. Let's take a look now at the signals. Okay, so this chip is the right chip now, used to be the left chip. If I'm going to touch data bit 0, this was one that was screwed up originally. Oh, and it's working, but not well. What is going on there? That does not look right. Why is it changing? Let's turn it off and on. Something is wrong there. Pin 2, which was fine, looks screwed up still. 3 was okay before, and it is still. That one's bad. Bad. And that's bad. And that's bad. Okay, so it looks like the problem didn't really move with the two chips. So swapping those kind of confirms that the RAM chips are probably okay. Now, unfortunately, I don't have a way to test these. Some SRAM chips you can test in the TL866 MiniPro, but not these old 128-byte ones. These are chips from the 70s. These are so rare to find just because even when this thing came out, they were ancient technology. I think it's time to focus on these three ICs. Let's see about swapping these out. I'll do it one by one, and we'll see if anything changes. So these are all the ICs that were sent in by Team Maloney from the last mail call, and I happen to have the three that I need. LS244s, I actually have 2 of those. I have a 373 and a 245. So let's just use these parts to swap these out and see if anything changes. Oh, and the nice thing is the date code on all of these is old. This is 82, 81, 82, and 81. So I'll be putting very similar vintage chips back into this board. First, I'll start with the 245 here. I'll pop that out. Now, fortunately, these legs are a little bent, so I will have to just adjust these. Okay, the first 245 is in. Let's turn this thing on. Still not initializing, but let's see if things look different on the oscilloscope. Not good. Okay, no change at all. So it definitely appears this 245 that I took off is original, so I'll leave it off for now, but I'll end up switching back to that just to put the original parts back on this board. I actually have a change of heart. I'm just going to take these ICs all out. So these are the 2 original chips here. Actually, these are the 3 original chips. I'm just going to pop this one out as well. I'm going to see what this computer does when these chips aren't even in the board at all. None of them are going to be installed. Okay, one thing that's interesting is when you turn on the computer now, the sound starts changing. Listen. It's like it's phasing a little bit. And that's probably because the sound chip is on the other side of these chips. So I think that's happening because with these chips removed, this is now isolated. The sound chip is isolated, and it's just seeing random junk on the data bus, and it's, of course, causing the sound to change. But that's fine. Let's take a look at how this looks now on these data lines without these chips installed. That should be bad, and the next one should be bad as well. And it is. I think I'm just going to take the RAM chips out entirely. And we're going to look at those data bus lines without these chips even in here. At this point, there's not a whole lot that could be wrong. With these chips out and the RAM chips out, it leaves us with the ROM chips and the CPU. The video display processor is also on the bus, but the fact that we tried two different chips and it didn't change the way the data lines look leads me to believe that it's something that's left. But let's just quickly check without the RAM installed and see what these lines look like. It's going to look, now it's not going to look exactly the same, but let's just see what this looks like and maybe I can learn something from it. Yeah, so this is one of the lines that's always been stuck low, and it's still stuck low. That one looks a bit weird, but that's how it looked with the RAM installed. Yeah, really, things are looking basically identical. That's weird. Why was that signal there a second and then gone? Okay, so the RAMs are out, but the LS245, 244, and 373 are in. And what the heck is going on there? I'm not moving the oscilloscope probe around. It's just stuck in one of the pin sockets. And what is going on here? That's just screwed up. You should never see, this cannot be right. There's no way that this behavior is correct. It should be rock steady, just like this signal right here. Or this one. Even though it's, got some bumps on the top and bottom, this is okay. That's not bad. And when I turn the computer off and back on, look, it's sort of all over the place. So I think at this point I need to pull these two ROM chips out. These are 2532s, which are similar enough to 2732s that if these are bad, I can hotwire a 2732 EEPROM into these sockets. There's just a couple pins that have switched around. So I'm going to pull those out right now. Well, you can see that I have these sockets installed in the board, but I've gone ahead and tested, and yeah, of course, with these ROMs in there, it's not working. But when I pull the ROMs out, it kind of looks like the problem goes away. I won't show the oscilloscope results, but the computer also is not doing anything anymore because, of course, the CPU needs the ROMs to try to do something. So it sits there trying to read the ROMs out. And of course, they're not working, so everything is just sort of dead. And this leads me to this part of the basement, which you don't see very often because I don't normally film over here. There's sort of stuff piled up randomly. My 3D printer is here. But I have this 286 set up. It's currently running on this monitor. I have my Zeltec MiniPro programmer connected to this PC. This is a PC interface type of programmer, but it's old, and so it supports older chip types that the TL866 USB programmer doesn't support. It connects through an ISA card on a 286 or an XT, and it has to be a slow machine. It does work on newer machines like a 386 or 486, but the problem is if the clock speed is over 10 megahertz, which is states in the manual, you get all sorts of communication errors and problems. So I have this 286 motherboard here running at, I think, 6 megahertz or 8 megahertz, and it is absolutely working fine on this. The reason I broke this out is because this supports reading and writing to 2532 EEPROMs, which are pin compatible with the ROM chips that are on the TI99. So I put one of the two ROM chips into here from the TI99. Let's see if we can read this out. So we're gonna go over to device and we're gonna say read, and we're gonna read the whole thing. It's only 4K, read successful. We're gonna go to buffer and let's take a look at view. We got absolutely nothing. Yeah, it went up to FFFF, so that's the whole buffer. And there's nothing there. Let's just try reading that one more time. Read. It says read successful. And view, nothing. Okay, I'm going to swap out to the other chip here. This is the other ROM chip. And we'll go back to device and we'll do read. Read success. Nothing. The buffer is empty. All right, just in case we think there's something wrong with this programmer, because I haven't used this a whole lot, I have another EEPROM here. This is one I got in the mail call. I think this was the Moss one from a 1571 disk drive. So we'll stick that into here, like so. We will need to change the device type. 27128. I'll say device read. And it's bigger, so it's going to read from 0 to 3 FFFFF, or 3 Fs. Here it goes, it's reading. This programmer makes kind of a high-pitched noise, if you can hear it while it's reading. Success. And we'll check the buffer. There it is. Well, so it seems like the two original ROMs are bad. I mean, this thing's not able to read them. The computer's not booting up. So I'm going to go off the assumption that they are bad. And to that end, I have two 2732. So these are 2532 equivalents. These are 2732 EEPROMs. I've erased these. I also got these with the mail call. Now the pinouts on 2732 EEPROMs are similar, but they're not the same. So I will need to make an adapter to use these. But I'm going to program these with the ROM image of what was on these, and hopefully if I stick these in with an adapter, the computer will work. And here we go. I'm going to hit P for program device. Do you want to program? Yes, I do. It's doing something, but it's certainly going very slow. Oh, wow. It's going to program this thing very slowly. Do you hear the noise this thing makes? That's actually coming from the programmer itself. I think what it does is it's probably getting 5 volts from the ISA bus, and then it's using DC to DC converters to step up the voltage to whatever it needs. And obviously the coils and things in here are quite whiny to produce the 21 volt programming voltage that this thing needs. So I've printed out the pinout of the 2535, which is the original ROM chips. If they were EEPROMs, they would be this part number, but they're a mask ROM, so of course it doesn't have that part number. And this is the pinout of the 2732, which is the EEPROM I just flashed. And when you look, the only actual difference is these two pins are swapped. 21, which is VPP on the 25, and A11 are switched around with A11 and Enable on this one. Now, when you look up the datasheet for the 2732, Enable just turns on the power to the EEPROM, and the actual chip select is this G with a line over it. Also, it's the VPP pin. And on the original ROM, PD and /program, pin 20 is the chip select on this. And if you look at the schematics for the TI, that's how it's wired up. VPP, which is pin 21, is just wired to ground, which is exactly what this needs on this E pin. So really, you just got to swap these two pins. So I went ahead and I made an adapter. So basically, on this side, it's just this side of the chip. All the pins are just connected straight through. But on the other half, I cut off the little pins on 2 of the pins, 18 and 21, and then I wired a little blue jumper wire between them to swap them around. And I made 2 of these, and the other one is already installed onto the EEPROM, just like that. So I'm going to put this one on here, and we're going to install them in the computer and see if it boots. You just want to make sure that it's the correct 2 pins that are swapped around. So I'm looking at the picture here, the notch is up at the top, and the notch is up at the top on these, and it's these 2 pins. So that is correct. Now, unfortunately, I'm not sure which of these EEPROMs is which when it comes to on the board. So I'm just going to install them in here and see what happens. Now it's a hilarious stack of chips, but hopefully if this gets it working, then we're golden. I've installed the 3 GROM chips in here and the 2 stacked EEPROMs. I put the GROMs in just in case it does boot. I want it to go all the way to the boot screen. I'm not totally holding my breath because it seems like everything I do come across a new fault. But hey, it might work, right? Okay, we're ready to power it on. Now, if it doesn't work, it could be the 2 ROMs are in the wrong sockets. I need to swap them. So don't jump to immediate bad conclusions if it doesn't work. But here we go. Ah, not working. Okay, I've swapped these around. Let's see what happens. No, it's still not working. Oh, this is not good. All that work. I think that's the end of my troubleshooting because I've moved a bunch of chips around. I've swapped the 2 RAM chips. And yet, when I turn it on, I still see the same kind of screwy signals on here. Like on this pin here, and when I turn the computer off and then back on, you get this kind of thing going on. So that's not the RAM chip because I've switched the 2 around and that same exact pin is doing it. And I know it's not the ROM chips because of course those are new, and I've taken out these 3 bus transceiver thing. That is isolated. I've swapped the video chip between the 2 that I have, and literally the only thing that's left that could be causing an issue that I'm aware of is the CPU. So I had a thought about these ROMs. So I built these adapters so I could use these EEPROMs in this motherboard. But there's something I could do actually. Remember, the adapter just swaps around 2 of the pins on the EEPROM, which makes it compatible with the motherboard pinout. These are 2732 EEPROMs, which are fully compatible with being read, not so much programmed, but read on my TL866 MiniPro. These original ROM chips are 2532s, which are not compatible with this. But what if I take these adapters that convert these sockets on the motherboard to be compatible with these 2732s and I plug them onto these EEPROMs? I should be able to read them inside the MiniPro, and that would actually allow me to read out the contents and compare it to known good ROM files, which I found on the internet, to see if these chips are good. All right, let's try this out. So these are the original TI99 ROMs that were in this motherboard. Let's pop this into the TL866 MiniPro. Whoa, oh boy, don't want to drop these on the floor. There you go, you can see how it looks in the socket. All right, so I just picked a random 2732 EEPROM DIP24, and let's read this out, see what happens. Well, definitely read something. So I have to load the original ROM files into the buffer of the TL866 MiniPro software so I can compare it to what's on this EEPROM. So I actually don't know which EEPROM this is, so I'm just gonna load 610 here. And let's see if it looks different. Okay, so it looks different than what we just saw. So let me load the other one, 611. All right, so there's the buffer loaded in. Now all I have to do is go to verify. And what that's gonna do, it's gonna read the chip and compare what it reads to the buffer that's loaded here. So let's try that. Verify. Verify finished. Would you look at that? This chip is actually good. Let me swap to the other chip. So to validate that the verification is working, I'm going to hit verify again without loading the other ROM image. And this should fail because, of course, this is the other chip which has the other ROM image in it. Right away, it pops up with an error. It says there's a value, and you can mark it. Well, anyways, verify failed 3991. I assume that means those are all bytes that failed. In fact, oh yes, it puts them in red if there's a difference. So let's open the other file, which I think was 610, and we'll hit verify, see what happens. Look at that, it verified. So that tells us that both of these EEPROMs are actually totally fine. And when I read them on that other Unipro programmer on that DOS computer, and it was coming back with all Fs, that was a problem with that software. So I haven't used that very much. I've used this thing a ton. So clearly I'm not quite up to speed on reading EEPROMs with that. And when I tried to read out 2532s, it didn't work. So really this just tells us 100% that these EEPROMs are working. At least they're reading properly from a content perspective. There could still theoretically be an issue on the output transistors on the bus lines, and when it tries to drive the bus, maybe there's not enough strength on those transistors to, say, drive the CPU and everything else on the bus, but it works on the EEPROM programmer. That is a possibility, but at least I know if they read properly, they are not totally dead. So I think at this point, what I need to do is get my other TI99, so at least I can confirm that the graphics chip is working properly, that I have 2 of them. I need to make sure they both work, because I know that if this is bad or having a problem, it can really affect this. But the fact that the ROMs are good means that it still could be the SRAM chips, or it could be the CPU that's bad, but it could also be some of the decoding logic, because the ready signal on here, I see it pulsing, but is that a correct ready signal? I don't know. So at this point, I'm going to take a break from this, and sorry this video didn't turn into an actual repair video. So really what you've seen here is that sometimes you can be troubleshooting and you can go down a lot of different paths and you think you're on the right path, and it turns out you're not. I did a bunch of stuff here that I thought was going to make a working computer, and none of it resulted in a working computer. What I could really benefit from were some clear schematics for the TI99. My eyes are blurry trying to stare at that really fuzzy, horrible schematic that's available. It's so bad because it tells you, look at chip U601. There are no markings on this board. So you have to try to figure out, looking at the schematics, you know, oh, is it this chip here that it's talking about? And then trace some of the signals. Okay, that's definitely that chip that it's referring to. It's some of the most frustrating troubleshooting I've personally done up until this point. So anyways, If you have any tips or any sources of better quality documentation on this, I would love to hear about it in the comment section. Otherwise, put your comments and your questions and suggestions down in the comment section below. Of course, hit that subscribe button if you want to subscribe to my channel. Of course, hit the bell icon if you want to be notified. And if you like this crazy video where I went on a goose chase and I went nowhere, I'd appreciate a thumbs up. Otherwise, you know what to do. You can hit the thumbs down. So that's going to be it for today. Thanks very much for watching. Goodbye.